Hey guys, today we'll be talking about the drag dilemma, and a bowl I guess. So drag is important because it's affecting everything that we do in everyday life, like this man who's suffering through a tornado, but more realistically, probably something more like a skyscraper, which has a lot of drag force on it, believe it or not. So it's important that we understand all this. Now, before we understand Newton's second law, which is, well, something that you need to understand the drag force, we first need to understand that why it happens. When I have a force that opposes another force, and it slows down, that's Newton's second law in a nutshell. Very dumb nutshell, yes, but still a nutshell. Here I have gravity, and I have drag, as shown on the figure on the right. One is opposing the other, and we say that the cumulative of the two is some kind of net force. When I take that net force over the mass, then I get the net acceleration, and over time that gives me final velocity, and over time that final velocity gives me final position. Thus, I could say that I could model it all and reverse engineer it to get the vice versa of all the others. The force of drag, the force of drag is proportional to velocity squared. That's intuitive. If I run, I feel a lot more drag force than walking. And if I scale out by b and say that's in the negative direction, say that the drag force is opposite to my motion, like say the drag is equal to negative bv squared. So with all that, we can make an observation where I'm going to observe a falling styrofoam ball. And from there, I'll make a computation with drag and without drag. And we'll compare the final results of the two. So here's quick conditions if someone wants to pause the video and see that. Here is the bowl. The blue line represents the height, and the purple line represents the y-axis, and on the bottom right is all the positions that we're taking while it's falling. And these positions will be compared with a computational model. Before we discuss the computational model, though, we must also discuss the coding. I know, it's tedious. In the initial conditions, as highlighted by the white arrows, we could see all of our initial conditions given. Well, that part's more obvious, and quite honestly, a lot of this code seems like basic English. But what's not basic English is this part, and this is the part that I really want to delve home. Here we have Newton's second law iterated underneath the time to say that's a function of time. Likewise, velocity and position are also a function of time, and that's logical, as well, Newton's second law and velocity and position are all dependent on time. Finally, we have the plot on the bottom, where we then compare the data from the plot and the observed. Here's a computation without drag. As you can see, it goes below zero. That means that the object, the styrofoam bowl, went below the ground, and that is certainly not good. It means that our drag is equal to zero, and in this model, it's not very accurate. When we account for drag, though, we get a much better result. Here, from experimental value, we determine that b is equal to 0.525, just from experimentation playing around with numbers, and it hit the floor in the allotted time frame. So, when I compare that to my actual observed model, we see that yes, our hypothetical model is indeed mostly true. When the blue is observed, red is theoretical. Now, in the midpoint, there's a 10 centimeter difference. This is caused partially due to lift, perhaps, or at least theorized, because there's a pressure difference between the inside of the bowl and the outside of the bowl that's causing some part of lift. But what's most probable is that the theoretical model is most likely wrong, because it was 80 grams instead of 8 grams in the initial conditions, thus giving us much to be desired. But despite these room for improvement, we could see that it's still a better estimate than our computation without drag. So now let's discuss terminal velocity. Terminal velocity occurs when gravity and drag are equivalent to each other, thus, since their opposing forces will equal to zero net force. As shown by the highlight in white arrow, this is the velocity terminal, where it's a flat line. The model with drag models this very well in comparison to the model without drag, as the model without drag only has one force, and thus, since it has no opposing force, will not equal to zero, like seen on the graph here. Now, let's also discuss another thing. Let's say that I threw the ball down at negative 5 meters per second, so that's my initial velocity. Now, if I adjust that b value so that the object hits the floor in that given time frame, then I would see that nothing really changed. The terminal velocity is largely the same, and my graph isn't really affected by much. However, let's discuss why I adjusted that b value, and why I should. If I don't adjust it, my object will be off the ground by 6 centimeters in the allotted time frame, so it's essentially levitating, which is not good. The old b value was 0.525 to make that happen, and velocity terminal is negative 1.22 meters per second. Now, when I adjust b value so that way it hits the floor in time, it's b is equal to 0.5 instead of b is equal to 0.525. My velocity terminal has decreased by 0.03 meters per second. So let's discuss the results. Terminal velocity is affected by b values and vice versa. Therefore, from the downwards velocity experiment, we saw that the inverse of terminal velocity was equivalent to b in some kind of proportion. And also, the gravitational force must be equal to drag, so therefore, the bigger the gravitational force, the bigger b value you have, because that means bigger drag. So that's why we have the equation b is equal to gravitational force divided by velocity terminal. So as a recap summary, we have the initial discussion about the net forces, how they're equal to those two opposing forces, gravity and drag, and then we put those input values that we saw from the observed of the styrofoam bowl into both the observed model and the theoretical being drag and no drag, and we compared the results of all of those output values, where we then discussed possibilities and results. Goodbye, and have a nice day.